We stopped at perpendicular bisector. Right, guys, remember this is not any kind of a bisector of a segment, right? It's a perpendicular bisector. We even have a picture right here. By the way, in this picture, which one is the perpendicular bisector? The line L or JK? Raise your hand if you think it's JK. The perpendicular bisector is the JK. How many people think it's the line L? You guys are correct. It is the line L that is perpendicular. That is a perpendicular bisector, because JK cannot bisect a line, right? Can a line be bisected? No, a line goes on forever, right? In both directions. So JK is the segment that line L is bisecting. Do you understand? So please be careful. When I show this picture, people see that, oh, JK is a bisector. No, it's the line L. That's why it's in red also. Does that make sense?
Yes.
Okay, so now from this, and the reason why we talked about all those vocabulary words and so forth is because we want to talk about this theorem. Somebody read this theorem for us. Theorem 4.5. Go ahead, sir.
The point lies on the perpendicular bisector of a segment, and the point is equidistant from the endpoints of the segment.
There you go. What does it mean? Here's a picture. Can somebody explain to us what this theorem is saying? If a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. You guys remember what equidistance means?
Yeah.
Equal distance.
It's from what? What's so funny? It's the distance is right, same, right, from point B and C. Look what we have here. We have line L is a perpendicular bisector of segment BC. Then any point on this line L, for example A, will be equidistant, which means from the endpoints. A is right equidistant from endpoints. So AB will be congruent to what? AC. How would you go about proving this? Jesse?
First, you have to prove that line L is a perpendicular bisector to line BC.
Actually, that's given to you. They're telling you that line L is a perpendicular bisector, and any point on this line L, for example, this A, is going to be equidistant from each endpoint, right? So, how would you go about proving? What would you need to? What would your key step be in order to prove this? If I want to show that AB is congruent to AC, I need to show that, Jesse.
You have to show that that triangle AXC is congruent to triangle AXB.
Exactly. All we need to show is that those two triangles, AXB and AXC, are congruent. Because if I could show those two triangles are congruent, I'm done, right? Because then isn't AB and AC the corresponding parts of congruent triangles? How would you then show that these two triangles are congruent? One person see it? I want you to discuss with your group. I'll give you time. Go ahead. What do you think? How would you do it? So how would you show that those two triangles, AXB and AXC, are congruent? How about Lara? What do you think?
Side angle side.
By side angle side? How so?
They already showed that BX.
Right, so that's actually a good point. Why is BX congruent to XC? Because look at what's given. It don't say anything about BX and CX congruent. How are they able to come up with that conclusion there?
The perpendicular bisector.
Right. Perpendicular bisector has two meanings. First of all, that the bisector is perpendicular to the segment. Secondly, what? It bisects, meaning it goes through the midpoint. Right? Very good. So because we know that X is the midpoint, right? Because the definition of perpendicular bisector, yes. BX is congruent to XC, okay? Now, that's only one part. We need two other, don't we? Lauren, what are the other parts we need here? AX is congruent to itself. It's sharing that same side there. And lastly, Jesse, what do we need?
You need to prove that angle AXC is congruent with angle AXB.
Exactly. In our head, we know it's obvious that, of course, AXB and AXC are 90.
Yeah.
So, but how do we know that they're congruent? Yeah.
Well, you say that it's perpendicular, and then I think there's a theorem that says if two lines, well, no, that's backwards.
If two lines are perpendicular, then?
If two lines are perpendicular, then they form congruent adjacent.
Thank you. Then they form congruent adjacent angle. That's exactly what you're going to use. Does that make sense? And so by side angle side, we're done. Are we okay? So do you see how we define the perpendicular bisector right before this? Because perpendicular bisector means AX is going to be perpendicular to BC, and you said it exactly right. You're going to use that theorem, right? If two lines are perpendicular, they form congruent adjacent angles, so we know these angles are congruent. Okay? Actually, you could say they're 90 and so forth and do it that way, but isn't that a lot faster? Okay, and then that's how you prove. Guess what our next theorem is going to be? It's going to be the... Okay, theorem 4.6. But it's going to be exactly converse, you guessed. So, by the way, guys, will the converse of a true statement always be true every time? No, but this case it will be. So somebody read this for us. How about? Yes, go ahead, sir. I'm sorry. Here we go.
If a point is equidistant from the endpoints of a segment, then the point lies on the perpendicular bisector of the segment.
Right. So this is a converse of the previous theorem. So if a point, for example, in this case, if a point is equidistant, so A, if A right here, that's why it's AB is congruent to AC. If a point is equidistant from the endpoints of a segment, then the point lies on the perpendicular bisector of a segment. Okay. So do you see what we're talking about here? If you happen to have the point that is equidistant from these endpoints of a segment, that point A must lie on the perpendicular bisector of BC. Yes?
Will the perpendicular bisector always go through the opposite vertex?
Would it always go through the opposite vertex? Scaling?
Yeah.
The point is equidistant.
Like in a scaling triangle,
Right.
there's a point that's like in the middle of one of the lines.
Right, yeah, so don't think of, yeah, exactly. But from that point, if you were to draw a triangle, it is always going to be an isosceles, right? The question is, if you have a scaling triangle,
Yeah.
that's not what this is talking about. We're talking about not a triangle, we're talking about a segment. If you have a segment, and you found a point that is equidistant from each of the endpoints, that point must lie on that perpendicular bisector. We're not talking about triangles at all.
Oh, okay.
Is that okay?
Because there's like triangles.
Right. If you were to connect from that point to the endpoints, yeah, you always get triangle. By the way, what kind of triangles do you always get if you did this? You always get an isosceles triangle. Exactly. Okay. Any question? Does this make sense? All right. So then how would you go about proving this? I want you to then again discuss this with your group. I'll wait for you. Any question? Go ahead. Yeah, Alfred, let me get rid. Okay, go ahead. I'll wait for you. Oops. Can I give you a hint? Guys, man, hold on. Hey, do you see this dotted line AX? Guess what that's going to be? Yeah, and what sort of auxiliary lines do you think you're going to draw? You're going to draw it so that it bisects the angle A. BAC, which means angle A. Right? So you could, that's going to be the, okay, go ahead. That's what you're going to do, okay? Also, you could draw this auxiliary line such that not only you could draw it that way, that's one of the way, or even easier it would be, anybody see how you could do this a little bit easier? Actually, you could make this auxiliary line a bisector of this angle A, right? Even easier would be if you let a point that goes through the midpoint of BC and just draw an auxiliary line. That may be a little bit easier. Does that make sense? That you could do too, right? Because in a segment, isn't there a midpoint? Right? Midpoint exists. And from A to that midpoint, draw an auxiliary line. That may be a little bit easier to actually go about. If you did that, does anybody see what we could? As soon as you do this, then X is your midpoint. And what can you say? Basically, we need to say that these two triangles are congruent, right? So BX is going to be equal to? And congruent to CX, right? Because if I made this X to be a midpoint, and you drew this auxiliary line from X to A to X, right? You have this side congruent, you have these two sides congruent, okay? And what about AX? Congruent to? AX, right? So what do you have? If you were to, what can you use to show that the two triangles are congruent? Yes, sir? SSS, side, side, side. Because if you make the X to be the midpoint, right? Right. If you, isn't that a lot easier? If you make X to the midpoint and draw an auxiliary line from A that goes through A and X, right? Yeah, go ahead, everybody, go ahead. See if you, ask your group members if they get that part. Okay, go ahead. All right, so who can explain to us who we just talked about? So how are we going to draw the auxiliary line? Raise your hand. Yeah, so how are we going to get X here? Yes, Joseph?
You can use like a really Asian
What?
No, Asian, I said. Not Asian.
Ancient, like old font.
Oh, not Asian.
Okay. From the ruler postulate, we could get X to be the midpoint of BC, can we not?
Yeah.
So then what do we do, Joseph?
And then we use that thinking where in between the 2 points there's always exactly
Yeah,
one
between
line.
2 points there's exactly one line. Then we're done, aren't we? We know that then bx will be congruent to cx, ax congruent to self. How do I know that AB is congruent to AC, class? That's given. So by side, what can we say? Triangle ABX is congruent to ACX. Question?
What's the ruler postulate again?
Okay, who would like to tell us? It basically says, you could set up a unit and then there's always a point between any
I
two
can tell
points.
ruler postulate
Go
right
ahead.
now.
Okay, here you
The
go.
2 points on a line can be paired with one with
Hey, you're looking at the book.
Any 2 points have 0 and 1.
So you basically are defining a unit. You're defining a unit system. And so through any 2 points, there's exactly 1 point. And then you're going to have a midpoint in these 2 points. And you're basically setting up a unit in a ruler. So that's why it's called ruler. May I move on? Okay, let's go to then next theorem. So before I talk about actually next theorem, I want to talk about this definition. This actually has a definition. The distance from a point to a line is defined to be, anybody want to guess what we mean by the distance from a point to a line? What do you think? How do you think we're going to define a distance from a point to a line? You ready? Because if you have a point, hold on a second. So here's a point right here, let me call it point X, R. And let's say I have a line like this, okay? How do you find a distance from a point to this line L? What do you think the distance will be? Raise your hand if you think. Because I could talk, what sort of distance is it this distance right here? Is it this one? Like what sort of distance are we talking about? Because how many points are there on this line? Infinitely many. So through this point to this line, there could be many, right, distance we could talk about. But this is the reason why we're defining it. Anybody have an idea how we're going to define a distance from point to a line? Andrea?
Using a perpendicular bisector.
Perpendicular bisector? You can't bisect a line. So you got the right idea.
I mean, like that point has a line that's like perpendicular.
Exactly right. So we're looking for, we're looking for a line segment that is going to be perpendicular to this line. So we're going to call that the distance. Does that make sense? Okay, so here is how we define it. Write this down because this is important because it will come back later. So here's a picture also. So how do we define a distance from a point to a line? Well, this is defined to be the length of the perpendicular segment from the point to the line. Or if you're talking about it to the plane, it'll be the perpendicular segment from a point to the plane. So it could be to the line or the plane, same idea. So write that down. That's important because we're going to use this to this will be used for our 2 other theorems that's going to come up in a minute. Okay? And of course on the test. Okay? So knowing that definition, we now come to this theorem. If a point lies on the bisector of an angle, so you got a point that happens to lie on a bisector of an angle. So imagine an angle and there's a bisector, okay, angle bisector. There's a point on that angle bisector. Then the point is equidistant from the size of the angle. Okay, what do you think this means? And why do you think we talked about that definition? Distance from a point to a line just before this. Okay? Now I'll show you a picture that represents this theorem. Go ahead, everybody, write this down and think about, see if you can understand what this is talking about. Therese, what do you think? What do you think this is saying here?
That the angle, the triangle BXP is triangle BYCP.
Basically, that's what it is. So very good. So let's see whether we can understand. Okay. All right.
She deserved it.
Yes. Okay. So good. So what we are basically saying is, so she has shown us how to prove this. But what is this theorem saying? Maybe it's too obvious. If I were to pick up any point on this BZ, what is BZ right now? This segment. It's the, yeah, this is the bisector of this angle, right? So now I picked a point P. Does it have to be this P represents any point on this bisector. Very good. And what we're saying is what? What are they saying? This P is then what? Raise your hand if you, yes.
The same distance from both sides of the angle.
Yeah, both sides of the, no. The P is equidistant from these two sides.
I said from the sides of the angle.
Oh, very good then. Sorry, I didn't hear it. You're right. So in other words, and do you see why we define the distance from the point to a line? Right? What sort of, which is your distance? The distance will be the perpendicular segment from P to the line, right? So this PX will be the distance, right? Because it has to be a perpendicular segment to the line. By the way, how many perpendicular segments could you draw from a point to a line? Just one. Does it make sense, right? There's a fixed distance. And P, of course, to BC, the distance from P to the line segment BC will be the perpendicular segment PY right here. And so Therese told us, in order to show that, all you have to do is then show these two triangles that are congruent. The PBX and PBY. Is there a way to show that these two triangles are congruent? Because if I could do that, then we're done, right? Okay. It's the same. Right? So yeah.
Like, are you asking like how to prove like BXP and BYP?
Exactly. If I could show that BXP and BYP congruent, then we're done, right? Isn't that right? Because then that would show that PX is congruent to PY. Correct? Okay. So who sees how we could do this? Therese already told us, but Nor.
Okay. So they're you can prove it by the angle side.
Right? Because?
Because they're both because XBP, YBP
Mhm.
are
Yeah, those two blue ones, right?
Yeah.
They're congruent right here, right? You
Yeah.
see? And then what?
and PXB and PYB are congruent.
Right.
They're both right.
So because they're both 90 degrees, right? Because by the definition of a point to a distance from a point to a line, we know it makes a perpendicular segment right here, right? So we know both are 90. Then what?
And
Well, so we only have two angles right now. Where's the side that we could use for this? Two people see it? 3, 4, 5. Who have not? How about June? So we have the two angles congruent. We need the third part, which is the side, right? If you want to use angle side. Do you see a congruent side? Yeah, BP. They're sharing this common side, BP. Does that make sense? So by angle side, right? Right, you gotta see it from here. This 90 degrees, this blue one, and then the side. You see how that's angle side? Angle side, right? Right? The two triangles are congruent. Therefore, PX is congruent to PY by what? Corresponding parts of. Very good. Guess what our next theorem is going to be? That's right. So here's Converse. Here's the converse for this. If a point is equidistant from the side of an angle, okay, and you see how the P is equidistant from the side of the angle, PX and PY, so that's given to us, that's congruent. Then the point lies on the bisector of an angle, so the P has to be on this bisector, okay. So what would be your key step to do this? So, okay, you're writing, I'll wait. Okay, think about this. How would you go about proving this then? Okay, who haven't I called? I haven't called Sarah. What do you think, Sarah? How would you go about proving this? By HL theorem, how many people agree with Sarah? How many people think HL will not work? How many people have a different idea? Turns out it is HL. You're going to be needing HL. Because, why? Who could explain why Sarah said HL here? Jesse?
Because PB is congruent to PE with PB.
Right, okay, so yeah, there's, okay, that's the hypotenuse, they're congruent. PX is congruent to? Yeah, the leg.
How do you know that PX is congruent?
Very good question. How do we know that PX is congruent to PY? Ryan? Just give him. Right? Okay. So listen. Can we focus here? Okay, class. So do you see how through HL, right? You have the hypotenuse, that's the common side. And then XP congruent to XY because that's given to us, right? And we could see the two triangles are going to be congruent. And of course, if two triangles are congruent, then we can easily show that BP is the bisector of ABC, right? Because by definition of angle bisector, right, these angles, right here, right, will be congruent. Any question?
No.
Okay,
Thank you,
are we good?
for teaching us.
Yes.
Okay, good.
Hold on.